Thank you. Let me start, as always, by thanking the organizers for letting me present my work. I also think it's appropriate to thank them for these days of really nice mathematics. I've been having a lot of fun. So since the day is almost over, it's probably appropriate. I'm going to talk about this thing that I've been working on along this year, which is, well, as the title says, a cohomology strategy for the integration of Lie2 algebras. But I think that I need to justify myself, like, why would I care about such a thing? And the reason because of which I started to study this, it's because I'm interested in the integration problem of a rather more general object, which are the so-called LA groupoids. And I came to realize that we don't really understand very well the Lie theory of them. For instance, there is no notion, like appropriate notion of what isotropy should be or what the structure of S fibers or whatever that object should have. But why in the first place to study such a thing, right? I mean, LA groupoids, well, I haven't told you what they are, but I mean, it could seem like a rather arbitrary thing to study. So I'm going to tell you very briefly what they are and try and justify why they are interesting to study and where the Lie theory that I'm talking about appears. So the context is these are, well, groupoid objects in higher categories. So a groupoid object is this thing that you are used to, which comes with a source, a target, a multiplication, and a bunch of diagrams which encode the actions of a groupoid. And then you replace each of these spaces by, well, the category that you're interested in. So in this case, it would be by Lie groupoids, and all of the structural morphisms are going to be homomorphisms of groupoids. And of course, if you've got one such thing, you could differentiate in a direction, and you would get, since all of these structural maps are homomorphisms of Lie groupoids, then you'll get well, Lie algebroid morphisms in this side. So an LA groupoid is going to be a groupoid object in the category of Lie algebroids. And of course, I'm interested in the question of whether or not these things are integrable. It turns out that these objects abound in nature, so I'm going to give you a bunch of examples, and, and that's going to be, well, my first justification for studying them. First of all, you can regard Lie groupoids as being like trivial LA groupoids, like zero LA groupoids. And of course, the counterpart is simply the unit groupoid version. And you can also take Lie algebroids as being one of such examples when you take the unit Lie algebroid. And let me just remark in this step that, well, I mean, the Lie theory of a Lie algebroid is going to play a role already. So the question that I will be interested in is not whether or not the objects are integrable, but whether or not there is a multiplication making the object here into a double Lie groupoid. Now, next sample is the tangent prolongation and all of its multiplicative subbundles, which are referred to in the literature as multiplicative foliations. And this side, I'm kind of cheating a little bit because this object in general isn't a double Lie groupoid, and that's actually one of the reasons because of which I drifted away from studying this integration process with the strategy of A paths, which, well, proved to be so useful for the integration theory of Lie algebroids. Now, next, yeah.
Why is it not a groupoid? Why is it not?
Well, there isn't always a multiplication here, making this thing into a. I can actually tell you. So the thing is, if you try and replace. So you've got TG, and you know that source simply connected and source connected Lie groupoid integrating this is going to be the fundamental groupoid, right? And the thing is that in general, what you are going to have is that at the top, the multiplication should be defined on this. But instead, what you start with is well, the composable rows of this thing, which is Tg squared, right? So the right integration for this object is Pg squared, and well, this is simply not equal. And from time, I mean, and it's rather wild. I mean, you can have. Well, I mean, they do have the same Lie algebroid, so infinitesimally they are the same, but there is, I mean, they can be bigger, smaller quotients, disconnected, so that's why. Now, next example is something that has showed up today twice at least in Fernando's and Mikel's talks, which are VB groupoids and VB algebroids, and these are interesting by themselves because they include, well, all of the representation theory of Lie groupoids and also two-term representations up to homotopy. Now there is this thing that if you start off with a Poisson Lie group, well, the cotangent groupoid inherits the structure of an LA groupoid. So there's a Lie algebroid structure here because the thing is a Poisson manifold, and then the fact that the Poisson manifold, that the Poisson structure is multiplicative, induces a Poisson, a Lie algebra structure on the dual. And that makes this object into an LA groupoid. And it's interesting because historically, Lou came up with the integration of Poisson Lie groups by looking at the integration of this object morally, right? And this example, well, it allows extensions. I mean, you can play the same game by looking at Poisson Lie groupoids and more generally to the Dirac multiplicative Dirac structures that Mikel introduced earlier today. Next, there's this example, which is well, a group acting on a Lie algebroid or a Lie groupoid in a compatible manner. It's not simply by Lie algebroid maps and Lie groupoid maps. You need to ask a stronger compatibility condition. Think of Hamiltonian actions. It's not enough to have action by symplectomorphisms. And this is, well, my second justification, like why care about studying such objects. I think, well, maybe if you're interested in Poisson manifolds with symmetry and you want to quantize them, for instance, and you want to look at whatever the symplectic integration of this object should be, then probably you should be interested in study such thing. But for the rest of the talk, I'll be focusing myself on this rather trivial example, which are LA groupoids and double Lie groupoids over a point. And these objects are known as, in the literature, as Lie2 groups and Lie2 algebras. And it turns out that they are equivalent to simpler objects, which are called cross modules. And cross modules consist simply of a structural map and an action by appropriate automorphisms that's compatible. I mean, making this diagram, making this structural morphism equivariant and well, respecting the structure somehow. And this equivalence between Lie2 groups and cross modules and Lie2 algebras and cross modules of Lie algebras is actually categorical. So it's simply because it's more economic to write things as this than as well, groupoids. So Well, as I told you, I drifted away from the path strategy because, well, it turns out that it didn't paid up. It wasn't fruitful because of this situation over here. So I started to look at what these appropriate notions of isotropy should be, and I realized that we don't actually understand when, like, I mean, one of the things that you could propose as an isotropy is making the pullback of a point of such a thing. And what you would get is, well, a thing that looks like the example of the integration of a Poisson manifold. And we don't know in general whether or not these objects are integrable, and they appear, I mean, they appear in the structure of a general double Lie groupoid in a rather, well, important manner. So that's why I wanted to understand when such objects were integrable. And since I, well, didn't have any notion of what they should be, I started by the simplest one, right? I mean, understanding what happens when I replace this G by a point. And that's why I focused on this. And this is what I came across. So say you start off with a Lie 2 algebra, and then this object is a Lie groupoid, so it's got a nerve, right? And then you can take duals and make the usual simplicial combinatorics, and then you would get this complex, which is the subcomplex of linear groupoid cochains, right? And of course, each of these steps is also a step in the respective Chevalier-Eilenberg complexes, right? And so, well, it turns out that there is a way of filling this, and that is taking appropriate subspaces of multi-linear alternating sub-groupoid cochains, sub-complexes of groupoid cochains on the powers of the Lie 2 algebra. And by looking at the cohomology of such an object, I realized that, well, the second cohomology classifies extensions. And let me give you like a quick proof. So if you want to look at the second cohomology, so you are going to take an element here and an element here, and the fact that it's a cocycle tells you, well, that it is a cocycle in the Chevalier-Eilenberg cohomology, which means that, well, it represents an extension in the H direction. And then this condition here is telling you that the map is not going to depend on the base. And this compatibility condition here is going to tell you that, well, this fits into an extension. And, and well, I mean, one would need to see that this is actually up to isomorphism, but, well, it is also as an extension of the usual theory of Lie algebra extensions. And so if you have studied integration, this should ring a bell because of what's been referred to as the Van Est strategy. And the Van Est strategy is a classical strategy for the integration of Lie algebras, which starts as follows. So you suppose that you've got a Lie algebra that has a faithful representation, and then you can regard it as a Lie subalgebra of a linear Lie algebra. And of course, the linear Lie algebra is integrable. That's part of the deal. And so it is integrable as a sub-object. Next, you suppose it isn't. You suppose the adjoint representation isn't faithful, and then you get a kernel, right? And this is an exact sequence that, because of the classical theory of extensions of Lie algebras, can be codified in a 2 form of the Chevalier-Eilenberg cohomology of the image of the adjoint representation with values in the kernel. Now, the image continues to be a sub-algebra of a linear Lie algebra, so it's integrable. I'm going to call it G. And then there is the Van Est math, the Van Est theorem, the thing that is important, which says that, well, if the group that you started with is connected enough, then the map that differentiates cochains is an isomorphism for the degrees that I'm interested in. And you see, well, this can be rephrased, again, just for the economy, to say that the mapping cone of a map has trivial cohomology up till the step that I am interested in. And using this, and the fact that, of course, I took the simply connected integration and these things are Lie groups, then the thing is too connected, and then this form omega came from a form in the second cohomology of a group, and, well, this represents an extension, and therefore, well, we built an integration of the Lie algebra that I started with. Now, the whole plan is this idea prompted me to look at what cohomology with values in a representation should be, so that I could look at extensions of Lie to algebras, right? And the classical philosophy for looking at representations is just take them up onto the endomorphisms of the flat abelian object. In this case, the flat abelian object is the so-called two-vector space that's simply a Lie2 algebra, but brackets are 0. And since this is a category, there is a natural space of endomorphisms, right? Which is, well, the category of linear subfunctors and linear natural transformations. And it turns out that this comes with an additional structure that is sitting there and nobody uses, which is the horizontal composition of natural transformations. And this thing turns out to be associative and multilinear, and therefore, well, you can build a Lie bracket by taking the usual commutator of the horizontal composition. And with that, and in the language of cross modules, this is what appears. And notice that the bracket downstairs is going to be, the bracket inherit as a subspace of GLW and GLV. So when I define a representation in the next slide, what I'm going to have is, well, a morphism which includes two representations of a base on the two spaces that I've got here, but then some additional information that is going to, well, measure. I'm getting ahead of myself. So let me give you examples of representations. First example, of course, is the zero map. The zero map is a representation of Lie algebras. If you start off with either W or V equal to 0, then you get an honest representation of a leaf space of a Lie2 algebra. And there is a good thing that there is an adjoint representation, which extends the usual adjoint representation, and well, it's going to play a main role in what follows. Now, the fact that there exists an adjoint representation takes, yeah. Okay. So having an adjoint representation gets us one step closer to using Van Est strategy. And this is because, well, among the ingredients that we needed were that we needed an adjoint representation, and then we needed that linear Lie algebras, in this case, linear Lie2 algebras, are integrable. And this is a good point to tell you that they are. Okay? And, okay. So now, in the presence of such thing, one can build a semi-direct product structure. And this semi-direct product, if you look at it, just, I mean, forgetting about the structure of Lie algebra, it is a VB groupoid over the Lie2 algebra that you started with. And therefore, it is a representation up to homotopy. And that representation up to homotopy is going to play a role later on. Okay. So this is a proposition that says that the ansatz, I mean, I started with this category of linear self-functors and linear natural transformations, but nobody said that that would represent anything useful. And this is saying if you start off with an extension of Lie two algebras and you split it, then you induce using, well, the natural formulas that you can come up with. This induces a two representation in the sense that I am telling you. So it induces a map into this GL of this two-vector space. And if you start off with an extension, an abstractness extension, and you split it, then you can use that splitting to replace this object in the middle by, well, the direct sums. And then you can rewrite everything, as you do in the case of Lie algebras, right? And when you do so, well, you get these formulas in which you've got semi-direct products where they are twisted by some forms. And these forms measure how far your splitting was from a Lie two algebra map, right? And they live inside of these spaces. So one question is, well, what happens if I start off with these objects? What kind of equations should they satisfy in order to define an extension of Lie two algebras? And it turns out that this is the proposition. Rather hideous, and I mean, it's not for you to read, but it's for you to get that it's horrible. And so what I would like to do is to get a complex out of which I can read all of this information as simply a cocycle condition. And of course, I can play the same thing for isomorphisms and replace it, and then realize that in order to commute, there are just two maps that are relevant, and the proposition, the analogous proposition is, well, other set of equations that I'm later on going to reinterpret as a cocycle condition. So out of exactly these pieces, I ended up building, well, a tragic object, which is a triple complex. And it's a triple complex because it isn't. I mean, it is a three-dimensional lattice, but unfortunately it doesn't commute in all directions. And the pieces of it are a bunch of Chevalier-Eilenberg complexes, which involve, well, all of the Lie algebras that are appearing, right, with the respective representations, and then combinations which involve the action by derivations that the cross module came with. And this is a general formula for that action. And if you have read the work of Hochschild and Serre on the spectral sequence, which is named after them, then you might be familiar with this object. This is the same representation that they use in that work all the time. And of course, since this is a three-dimensional lattice, there is an obvious way of grading it by counter-diagonal planes, just in the same way that one does when one thinks of the complex, of the total complex of a double complex. And as I told you, unfortunately, the square, if you take all of the differentials, the square of the differentials, unfortunately, doesn't go to zero. And that's because of some lacking of commutation in some faces of this three-dimensional lattice. And then you need to add these diagonal maps. But then if you look at the gradings here, you will realize that although they don't commute, they do induce a map of so see that all these maps are moving in the P direction and also in the Q direction. So that means that there is no problem of commutativity in each of these pages that are getting into the blackboard. So the pages that are going into a Blackboard are honest double complexes. And what these ratings are telling you is that although the thing may not be a triple complex, if you consider the total complex of each of these pages, then what you get in the end is an honest double complex. And in this honest double complex, the equations that we had before are exactly what I wanted them to be. Or the second cohomology of this triple complex classifies extensions. And of course, if I want to use this to integrate lead to algebras, I need to tell you what happens in the case of lead to groups. And the thing is, well, there is a way of integrating this. That's an object that I call GL phi. Maps into that define representations which are the right ansatz in that when you look at extensions and you split them, the action by usual conjugation induces one of these. And there is also a set of ugly equations that define when these extensions induce extensions of lead to groups. And they fit in a suitable triple complex, which is interesting because, well, this is this page for the triple complex of a lead to group, and it comes with, well, the group cohomology of the base, the group cohomology of the core, and in each of these directions, well, on the rows you've got Lie group bundles. Lie group bundles is the complex of a groupoid of these successive Lie group bundles with values in a special representation, and each of the columns is the action groupoid, are complexes of the action groupoid. So you see, there is some underlying structure that we were looking at before, as some interplay between the core and the base, which comes with this action, for instance, which, I mean, in general, cannot be extended, but there are a bunch of examples of double Lie groups, of double Lie groupoids, where this can be done. And then if you look at the natural map that takes one of these extensions and of Lie to groups and gives you an extension of Lie to algebra, then, well, you're bound to call this thing a Van Est map. And this map is built out of, well, doing the antisymmetrization in separate coordinates for the nerve part of the groupoid and this core that is appearing everywhere. These are the usual maps that one uses when defining Van Est. So it's taking left invariant vector fields and looking at level curves of a map. Now, the fact is that when there is when the representation that I'm taking is on an honest vector on an honest vector space, so not a two vector space, but an honest vector space, then there is this Van Est map. So I can tell you how the proof goes, because if you look at this map, when there's no W, I mean when there is just W0, which is V, then each of these maps are going to be the usual Van Est maps. And therefore, if I look at the mapping cone of a thing, I will have, of each of these maps, I will have this double complex whose cohomology measures, well, where the thing is inducing isomorphisms, just in the same way as in the case of a classical Van Ness map. And well, I can look at the spectral sequence of this thing, and you see, since I already have the connectedness of H, I know where this is going to be 0, and using the QNet formula, I know, and the connectedness of G, I know where all of these are going to be 0, and well, it turns out that it's going to be 0 below the diagonal, so the result follows. And as a corollary of this, there is this cute result, which is that if you start off with a Lie-2 algebra for which the centralizer of the unit is transversal to the core, then the thing is integrable. And the proof is, well, if you look at the adjoint representation, the part, I mean, the adjoint representation is an honest vector one, is an honest vector space, and then you go through the whole Van Ness program, and that's how you integrate. So let me just summarize again what happened. So we've got adjoints for these objects. We've got integrability of a linear Lie-2 algebra. We've got a cohomology theory, well, 2 cohomology theories that classify both extensions of Lie-2 algebras and Lie-2 groups. And, well, I've got a partial Van Ness. For the general Van Ness, though, I know that the map can be factored as this map, which is the Van Ness map of Lie groupoids. And therefore, because of the theorem of Marius-Krajnik, this is going to be an isomorphism in cohomology depending on the connectedness of the S fibers, which in this case are going to be H. So I'm exactly in the same situation. Now, the only question is what happens here, and I still have no clue, but I'm hoping that, of course, that depends on the connectedness of G, and hopefully in a manner that lets me guess what's going to happen in the more general situations, which is my last comment, actually. So although all of this may seem rather ad hoc, because, I mean, I was using all the time, well, the language of cross modules, it is not. Most of these structures, with the remarkable exception of the adjoint representation, naturally, can be extended for rather general classes of double Lie groupoids. And so once I finish up with this program here, I'm hoping to get, well, an integration result for some other class of double Lie groupoid. And that's it. Thank you.